All right, let's talk about a data structure that sounds way more complicated than it actually is, the linked list. Seriously, by the end of this, you're going to see just how simple and clever this whole idea is. In fact, you know what? Here's my promise to you. After we go through this, you're not just going to get it, you're going to be sitting there thinking, wait, that's it? That was actually easy? So let's dive in. And to make this super clear, we are not starting with a bunch of scary code or technical jargon. Nope, we're going to start with a simple story about a very clever thief. So picture this. A thief finds a piece of paper on the ground. It's got one address on it, house number 9. So he goes there. Inside, he finds some gold. Pretty cool. But he also finds another slip of paper with the next address, house number 2. So what does he do? He follows the clue. At house number 2, same deal. More gold and the next clue, which leads him to house number 7. He just keeps following this chain of clues from one house to the next until he gets to the last house. And inside this one, there's just a final note that says null. That's just a fancy way of saying, end of the line, pal. The heist is over. Okay, kind of a fun little story, right? But what on earth does the thief's treasure hunt have to do with computer science? Well, as it turns out, this story is the perfect blueprint for understanding a linked list. This is the moment where it all clicks. See, every house in our story, in the tech world, we just call that a node. The gold that our thief was collecting, well, that's simply the data that we want to store. And that really important slip of paper, the one with the next address, that's just a pointer that we call, well, next. So let's break that down. A node is really just a simple container, like a little box with 2 compartments. The first part holds your actual data, could be a number, a name, whatever. The second part holds that magic pointer, the address that tells you exactly where to find the next node in the chain. Okay, that's enough theory. Let's get our hands dirty, so to speak, and see how you would actually build one of these chains from scratch. All right, let's start with the absolute basics. Imagine we create 2 nodes. We'll just call them node A and node B. Right now, they're just floating in space, completely separate. They don't even know the other one exists. Now here comes the magic. We take that next pointer that's inside of node A, and we tell it to point directly at node B. And bam! Just like that, we've created a link. They are now connected. A knows where to find B. And you know what the best part is? The code to do this is ridiculously simple. In most languages, it's just a single line. Node1.next equals node 2. That one little assignment creates the entire connection. It's that easy. So we've got the visual, we've got the basic command. Let's see how this actually looks when you write it out in a little bit of Java code. Don't worry, it's not scary. In Java, just like in construction, before you can build any houses, you need a blueprint. In programming, we call this blueprint a class. We're essentially just drawing up a plan that defines what every single node is supposed to look like. And our blueprint is super simple. All it says is that every node we create must have 2 things: a place to hold some data and another special spot called next, which is built specifically to hold the address of another node. So once we have that node class blueprint, actually making the nodes is a piece of cake. It looks just like this. We're just telling Java, hey, use that blueprint to build me a new node with the data A, and then do it again for B. And how do we connect them? You already know this part. It's that exact same beautifully simple command we just saw. Node1.next equals node 2. That's it. We now have a real functioning linked list with 2 nodes. Okay, so linking 2 nodes is easy, but what happens when you have thousands? How do you even keep track of all of them? Well, this leads us to the single most important rule of linked lists, the head rule. Let's just zoom out for a second. Our little 2-node list is simple to manage. But what if you have a massive list? Let's say 10,000 nodes long. Are you going to create 10,000 different variables in your code to remember each one? No way. That would be a total nightmare. So how many of those 10,000 addresses do you actually need to remember to access that entire chain? The answer is kind of mind-blowing. It's just 1. This is the key insight. To have control over the entire list, you only need to keep track of the address of the very first node. That special starting point has a name. We call it the head. Think about it. The head is your key to the whole kingdom. If you want to get to the 3rd node, you don't need its address. You just start at the head and hop along the chain. Head.next.next. You can get to any node you want just by following the pointers, exactly like our thief followed his clues. And that's the real magic here. You can manage a massive list while only ever having to keep track of one single thing. So, now we know how to build a chain of nodes and how to walk it from the beginning to the end. But you might have noticed it's a one-way street, which brings up a really interesting final question to think about. What if you needed to go backwards? Is it even possible to reverse the chain?